Good morning, good afternoon, and good evening to everyone joining us online. Welcome to the keynote lecture of Data Excellence Week 2026, organized by the Chinese University of Hong Kong Library. Today's keynote title, Data, Research Libraries, AI, Enhancing Services Through Technology, will be delivered by Dr. Peter Broadwell from Stanford University Libraries in the United States. My name is Xinxin Zhang, and I am the Research Data Librarian here at the CUHK Library. I'm delighted to be your host today. We're excited to present our annual flagship event, Data Excellence Week 2026, a week-long program dedicated to advancing awareness and best practices in data sharing, management, and reuse. We are especially pleased to welcome participants from CUHK, institutions across Hong Kong, and many other parts of the world joining us virtually today. Welcome. This lecture is being recorded and will be shared on the CUHK Library's YouTube channel later. We'll hold a Q&A session towards the end of this lecture. Now, it is my great pleasure to invite our university librarian, Mr. Benjamin Meunier, to deliver the opening remarks and to introduce our distinguished speaker. Thank you very much, Ben.
Thank you, Chin, and allow me to reiterate to everyone a warm welcome for joining us online, whether it's morning, afternoon, or evening for each of you. You're very welcome, and we're delighted to have you here for the keynote lecture of Data Excellence Week 2026, which is organized and hosted by the Chinese University of Hong Kong Library. At CUHK, we're deeply committed to advancing the role of research data, both in its effective use and in its responsible management. This year marks the second edition of Data Excellence Week. The week is designed to raise awareness of sound data practices and to highlight the growing importance of data across disciplines. Over the coming days, participants can look forward to a rich and engaging program, including faculty panel discussions, best practice sharing sessions, student project presentations, and of course, today's keynote lecture. From the faculty panel and best practice sharing sessions to the Data Champions inauguration ceremony and the final presentations of the Data Analytics Practice Opportunity, the Data Excellence Week 2026 program showcases CUHK's continued efforts to promote excellence in data management and data reuse, both on campus and beyond. Each event during the week is designed to offer practical skills, fresh insights, and diverse perspectives from both students and faculty. Our goal is to foster a culture of excellence and innovation in research data, encouraging the CUHK community to share, engage with, and make meaningful use of data in your research, teaching, and learning. Yesterday, we officially opened Data Excellence Week 2026 with an online panel on cross-regional perspectives in research data management. We had the privilege of hearing from Professor Marilise LaRose-Hill of Cape Peninsula University of Technology and Professor Terry Yip of the Chinese University of Hong Kong, who shared valuable best practices in research data management drawn from their respective research communities. After today's lecture, we have a series of exciting events lined up for the rest of the week. To explore the full program, please visit our website using the QR code which is displayed on the screen or the link which is provided in the chat box. We warmly invite you to join us in celebrating Data Excellence Week 2026 and to take part in the diverse activities we've prepared. Together, we can deepen our understanding of research data, strengthen its applications, and drive innovation and excellence across our academic community. Today, it is our great privilege to welcome our distinguished keynote speaker, Dr. Peter Broadwell from Stanford University Libraries in the United States. Dr. Broadwell will speak on the topic of data, research libraries, AI, enhancing services through technology. I had the pleasure of introducing Dr. Broadwell only a few weeks ago for an event hosted by the Pacific Rim Research Libraries Alliance, and it's always a pleasure to learn more about our distinguished speakers, and I learned more about Dr. Broadwell in preparing for today's session. Dr. Broadwell is the head and technical lead of the AI modeling and Inference group in research data services at the Stanford University Libraries. He has a PhD in musicology from the University of California, Los Angeles, UCLA, where his dissertation explored musical depictions of pirates and bandits in 18th century British theatre, which sounds fascinating, and also holds a Master of Science degree in computer science from the University of California, Berkeley. At Stanford, he leads a team of research developers who collaborate with faculty investigators to explore novel applications of emerging AI and machine learning techniques in diverse cultural domains. Dr. Broadwell previously worked at Stanford as a digital scholarship research developer at the Library's Center for Interdisciplinary Digital Research from 2019 until he assumed his current role in 2025. Prior to joining Stanford, Dr. Broadwell was an academic project developer in the Digital Library Program at UCLA, where he contributed to research projects in digital folkloristics and cultural analytics of Scandinavia and East Asia, and also to library-based investigations of the relationships between social media, television news, and web content. All this to say, we are really delighted to have such an expert with such a broad range of interests. Dr. Broadwell, without further ado, the floor is yours, and participants, please join me in welcoming Dr. Broadwell.
Well, thank you, Mr. Meunier, and for that wonderful introduction, and to Chinchin for the invitation. I am delighted to be presenting this keynote lecture at the Chinese University of Hong Kong Libraries Data Excellence Week, and I will share my slide. All right, please let me know if there are any problems with the presentation, but if not, I will begin. Here is a quick outline. I will begin by providing a bit of an overview of how what we think of research data services at Stanford, which encompasses, as you'll see, research data management practices and services, and quite a few other related services. And of course, as you saw from the title of this entire talk, but the overall focus is to discuss how research libraries can enhance their services through data, AI, and deployment of technologies around those particular areas of focus. So after this kind of information sharing session about how research data services at Stanford have been constituted, then I'll move into a series of case studies involving projects that I've been involved in to some degree here at Stanford, primarily focusing on AI and data services. You can see a listing of them there. I think I'll get through all of them. There'll be discussions of scientific data extraction, GIS, map data, working with images and text. Also some music, some even piano music, and also very old computers. And finishing up with some discussion of the performing arts, of archives of the performing arts. And then should hopefully be plenty of time for questions. So if anything comes up that you're curious about or like to ask about or correct me on, I welcome such feedback at the end of the talk, or anytime during the talk, actually. But for now, we'll continue on to my first slide. Next slide. In this overview of research data services at Stanford, this slide is really just to point out that we do have a website that provides an overview for patrons, students, researchers, research faculty, postdocs at Stanford, to give them a sense of the research data services that are provided through, well, the Stanford University Library specifically. And if you follow this URL, you can find a page that has these graphics on it and a bunch of other things. So yes, you'll see what should be a fairly familiar circle of the research data life cycle, which is still a very important conceptual frame for the full services at Stanford. And then further series of links in the form of more or less a libguide indicating where patrons can get help with any of these phases of the research cycle through the libraries or affiliated units. But actually, for this talk, I thought that the audience might appreciate a bit more of an overview, specifically of the division of the library in which I work, which is named Research Data Services. And it's to some degree a subset of this entire research data support ecosystem at Stanford. But it's kind of an interesting phenomenon. It's a fairly new department or division, actually, that was established about 5 years ago by pulling together people from other divisions and hiring and a few new hires. So you get a bit of inside baseball here about how it was put together. So this it's a fairly small division. It's about a dozen people with an assistant university librarian at the head. And it's sort of broken into these small teams that fulfill various tasks and services around research data. But this is really just a small piece of all of the services in which we're involved, in which my division is involved. So I'm going to bring in a whole a larger set of icons as well in a different color in blue. So these are all of, or maybe not all, but a good number of the units outside of research data services, but still within the Stanford University libraries that are involved in research data services and with whom the members of my division interact to provide various services. And I think just by looking through this org chart, I know it's a bit technical looking. But I think you can begin to get a sense of the overall goal, overall objectives of this particular division, and then also the general services that we provide. I would say the general defining characteristic of research data services, my division, is that we are primarily the boundaries of this division are more or less defined as encompassing the staff and services who work with data rather than being charged with provisioning, curating, and storing, primary sources of data, born digital or otherwise. So having our task defined this way, the charge of our department defined this way encourages us, or requires us actually to work with many other library units who fulfill the other roles of actually providing data, storing, preserving it, and often sharing data as well. So while allowing us to focus on services, the services that are sort of attached to data resources. So we can see that here. I'll just start with the green rectangles. These are the sub-departments here. In the upper left is probably the most specific to research data services. This is the group that was primarily hired after the division was created to fulfill some needs that we saw that we viewed as emergent and important to our mission. So this is data management services. Currently 4 people with a manager of data curation services and a research data curator who is also on the library track, so has a librarian title. And then 2 data curators who focus on specific general subject areas. Or not specific subject areas, but areas of modes of scholarly inquiry, you could say. So the first one is interdisciplinary sustainability. This is actually connected to our Dorr School of Sustainability, which is a brand new school that has been created at Stanford in the last 5 years as well, through a very large gift and lots of faculty hires focused on environmental sustainability, which is a field that requires a lot of data, whether it's remote sensing satellite data or scientific observations. So we thought it was important to have a data curator devoted specifically to that. This person also does work closely with our science data librarian, but we'll talk we'll talk more about what she does in a minute. Then there's also a data curator for programmatic access, who is someone who manages and is an expert in all kinds of data access via basically APIs. Accessing disciplinary repositories and other services across many disciplines, generally scientific disciplines, and a few other, well, mostly scientific data sources, but there are other resources in more relevant to social sciences and humanities that also provide programmatic access. So this data curator focuses on that as well. So that's the data management services group. We have a very important sort of central consulting and teaching unit which we call data science training and consultation, that is really directly facing students and faculty. So when students and faculty come to the library with questions about accessing data or working with data, actual data analysis, data processing, we provide a consulting service for that. And we have one staff member who kind of is the intake, in addition to managing a series of workshops, which are growing quite popular, especially among the postdocs and medical researchers on campus, a series of workshops on common technologies that researchers need to work with data, just things like Python and R, and data visualization and text mining. So in addition to running that kind of workshop series, our head of data science training and consultation also triages all support requests that come in. And actually, we have a staff of graduate student consultants, mostly in the sciences and social sciences, who are also able to then take on these requests. Occasionally, a request needs to be handled by someone outside of this group. So that's why we're a well-connected division. If a problem involves AI, or if an idea from, say, a faculty member involves AI and data, especially data at the library, that could come to my group, the AI modeling and inference group. So I'm over here along with our developer, my fellow developer, and I'll be talking a lot more about what we have been doing in the last few years in later slides. So I'll leave it there for now. There's also a geospatial center that was included in this research data services group, with two staff members. I'll point out that they are closely affiliated with the David Rumsey Map Center, which is a very well-resourced center with a great collection of historical maps. Although our geospatial experts and also our maps librarians in the science library also provide a lot of the services around, like I said, as I mentioned before, sustainability-related research resources, including remote sensing data and other GIS resources. And then finally, not finally, but getting towards the end of the list here, we have a set of academic technology specialists in research data services who are more facing towards humanities and social sciences. You can see the departments there. They're actually 50% time supported by academic departments and 50% time by the libraries. So they're sort of embedded in academic departments and are a direct conduit for research questions and requests from faculty members in those departments to the libraries. And of course, those requests may eventually find their way to the data science consultation group. They may find their way to the AI group or the geospatial group. But that's how the academic technology specialists group, that's sort of their charge. And they also work very closely with these external units, or I should say they're still internal to the libraries, but external to research data services. On the right, the groups in blue on the right here, including the social sciences research group, the humanities and area studies resource group. These are the subject specialists, the selectors, and subject librarians in those areas. Also our special collections department, and several other branch and coordinate libraries, which you can see listed here in the lower right. And then the other piece, moving to the left, which happens to be the more technical scientific side of this org chart, We also have our science data librarian, who works very closely with our digital library systems and services team. This is a large team that has developed our certainly our catalog and exhibit system, SearchWorks and Spotlight, and also Earthworks, which is our geographic information catalog system. And probably the most important for research data services is the SDR, the Stanford Digital Repository, which is our institutional repository. That our science data librarian is sorry about that, is also directly involved in helping to manage and develop, because it is an ongoing development on the SDR is always ongoing. That's what probably its most distinctive trait, I would say. The SDR was a quite early open source digital repository. It runs I believe we call it the Samvera stack of open source modules. I think it's based on Fedora, but with a lot of Ruby on Rails on top of it, and several microservices stood up on top of that. And it is where we, as with most institutional repositories, we encourage our faculty to deposit their publications and research data. And it's also where we put as much of the research data that we subscribe to as we can. And as well as all of our other digital collections that can be turned into objects, given DOIs and permanent URLs. And there are also a few other services around these materials, specifically that they can be indexed, obviously for search, if they're text, and also if they're images, made available via IIIF, the International Image Interoperability Framework. And you'll see how we use that affordance in one of the upcoming case studies. So I think that's it was worth dwelling on this slide for a while, because I think this shows how we have put things together here at Stanford. It's and to support what we have seen for the last, well, at least 5 years, as a growing need for research data management and support from the libraries. I do see some parallels to how the Chinese University of Hong Kong library organizes things, which is great. I think we could learn things from each other potentially, and yeah, it'd be a good conversation to have. But for now, I'll move on to the project case studies that my team and people affiliated with my team have been working on over the last few years. These will give some examples of how we can use the data resources available through these various units here on the org chart to, in most cases, to advance research that is both of interest to faculty members and also involving development of novel services, or at least augmentation of existing services in the libraries. So I'll just jump into the first one here, which is, yeah, so these are some excerpt slides from a talk that this group gave at the AI for Libraries and Archives and Museums conference at Fantastic Futures, it's called, in December of this year. So it's a fairly recent development. We're continuing work on this, but just full disclosure, this is where these slides come from. And want to give a lot of credit, especially to Simon Wiles, the developer in my team, who did most of the work on pretty much all of these, all of these projects that I'll talk about. But here we're also assisted by one of the academic technology specialists, Claudia Engel, who is in the anthropology department, and also Amanda Whitmire, who is the head of the Science and Engineering Resource Group, which wasn't even on that org chart I just showed, but has actually worked has been quite active in advocating for the provisioning of AI-related services in the libraries primarily to work with large quantities of scientific data particularly of a historical vintage. And to some degree, this interest comes about because of the presence of our marine biology library. It's a branch library that is based in Monterey Bay, very, very famous location for oceanography on the central coast of California. And particularly, it has many collections from the very early years of marine biology as a scientific discipline, including these intertidal zone surveys, by Ed Ricketts, who was one of the founders of the field of marine science. And he, over the course of many years, as you can see from the dates here, traveled up and down pretty much the entire west coast of North America, um, surveying the species he found in the intertidal zone, so the space between low and high tide. And he, as one of his several record-keeping systems, used these color-coded index cards, specially printed index cards, in which he mostly typed up observations on a typewriter. And this is important. This is an important collection, as are many held at the Hopkins Marine Station, which is where our marine biology library is located, because they come so much earlier than most observations of scientific observations of the oceans in this part of the world. As you can see from the graph here, there's 112 observations in the Global Biodiversity Information Facility from before 1950, and 21,000 plus after. And most of Ricketts' observations were, as you can see here, I should say all of his observations were before 1950. Ed Ricketts also features was a close friend of John Steinbeck, the author, and appears as the character Doc in a couple of his novels. And actually, Steinbeck did travel with Ricketts on his boat doing some of these observations. So these reference cards are digitized. They do have to be for us to work with them, or digitized or transcribed. In this case, we found the most expedient thing was just to image all of them. They're available as a collection in our digital repository. And as I mentioned before, you're able to view any image collection that has been accessioned there through IIIF. This is the viewer that you can see. It probably shouldn't be two up. It's a little bit confusing, but that's just a configuration setting that we can change. But you can see a little bit of what is going on in these observation cards. But just to highlight again, the goal here is really to add these observations to the full shared record for global biodiversity, specifically relating to oceans and coastlines in this case. So to do this, we're basically training an AI, or using an AI model, one of these large multimodal models that have come out in the past few years, to be able to just basically read these index cards. So each of the cards has a front and a back. The front side has information about a species that has been observed, and the back has more details about the observation, where and when it happened, and occasionally references to other sources. So we want to basically be able to go from the card on the left to the data record on the right. And this is actually an example of a record that we can get from this AI system once we've tuned it properly. We've done lots of prompt engineering and chosen different models and compared them to each other. I'll discuss that in a bit. But you can see how the data from the left makes its way into the structured, extracted scientific data record on the right. The title here does kind of point out something that happens, which is that occasionally the model will be more discerning than the actual record is. It decides that, there's an associated gravel flats with boulders could be the type of bottom of the ocean that we want to talk about. That wasn't necessarily a field that we thought we needed, but the model decided we needed it. So this is this is a workflow. We can't just run OCR, standard printed text recognition, mostly because the actual observations move around too much. There's not much handwriting here. If that was an issue, we would also need to do further handwriting recognition. But even so, just running regular OCR models isn't good enough. We need an AI model. So we're using this new transcription workflow that is, I think, becoming more common, or at least more familiar to folks in data science and libraries. But I think we found it important to really pursue a sort of principled design philosophy that would allow some of the tools we built to be sustainable and reusable. The problem with a lot of these tools these days is that the models are advancing so quickly that whatever you do can be outmoded or outdated very quickly. But we found that generally speaking, what doesn't get out of date is the need to do verification and review, and in some cases, correction of the and also evaluation of the bulk results you can get from running an AI assistant on thousands of these cards. We have to have some subset of human transcribed cards against which to compare the initial results so that we can discover where the models are doing things wrong and correct for them. So, and those approaches are generalizable across tools to some degree. And so that's what we're really focusing on in this project. So as we say here, we want to enable both human and AI involvement in transcription and review. We want to make this extensible to different card layouts. We actually have a very large set of anthropology records that are our next area of interest. As I mentioned, you need to be able to facilitate repeatable evaluation of the output of these automatic transcriptions and to support quickly, if a new model comes around, you want to be able to use that quickly and adjust, change the prompting system if necessary. So this is still work in progress. It's actually a little bit more advanced than in this screenshot now, but you can see basically this is our transcription interface where the findings or the extractions from the AI model are on the left here in this structured format, and we can see the original record on the right. And this is where humans can go in and correct any mistakes they might see. And this is just an example of one of these systems for evaluating the performance of an AI transcription model against the ground truth, and actually comparing multiple models to each other. So on the left, this particular piece of software is called Prompt Foo. It's open source software. We've actually customized it quite heavily here. So it's running these tests on these ground truth records. We can see the results with Gemma 3, which is the open weights version of Google's Gemini that we can run locally. There's a couple different versions of that model, and then Chanwen 3 vision language as well on the right here. So this is definitely an important part of the process to be able to compare models as they come out and decide which one we want to use, or maybe we want to use a couple of them and have them and compare the results from them. So those are some of the questions we're working towards answering now. So our findings so far. If anyone is doing this already, this may seem familiar to you, or maybe if you're thinking about doing it, this would be important to take note of. But certainly, different prompting strategies, but also the inference framework you use. Basically which library you're importing to run the model can actually result in differences in the outputs. So it's good to be aware of that and maybe figure out why that's happening. Obviously, you do want to think about how fast this takes or how long this takes to run. And if you're using a remote service, you'll have to pay for tokens. So you need to think about how many tokens you're using. And one of the core challenges here that we don't really want to gloss over is really just dealing with the fact that LLM transcriptions outputs are often subtly wrong. The models are pretty good at not making really big mistakes. At least you can sort of prompt those away. But then they start to do things that are very hard to notice. And this is a problem as well for humans because it's just hard to see what it's not always something you can detect. So that's like a problem where you can detect easily anyway. So that's a problem we're continuing to work on. I got a great question in the chat just about how do you search and find this data set. I mean, the cards themselves, if you go to one of these pearls like this one, you can find the cards. And currently that's all we have are the images. We're still in the process of transcribing them. So once we finish this project, we will make the data set available through the Stanford Digital Repository. We'll get a different pearl. And we'll go from there. Yeah. All right. So that was a first case study, focusing specifically on scientific data extraction with AI. Great. And so the next one is, yeah, as the title card says here, is about working with text on historical maps. This is primarily, I wouldn't call it an OCR necessarily, but an ATR task, so automatic text recognition, because it's a bit of like printed OCR, but also handwritten text recognition. Well, just basically we're trying some fairly cutting edge techniques to deal with the fact that text on maps is really difficult for a computer to read. You've got different font sizes, you've got text going in all sorts of directions. It's curved around. We've got like it isn't even recognized, but we've got a couple different very large scale text labels that are actually crossing over each other. Anyways, this is a good, but there are obvious benefits to doing this across a large historical map collection, like say Stanford's David Rumsey map collection, which has tens of thousands, if not hundreds of thousands of maps um, from the early 20th century all the way back to the 17th century. Um, and in particular, yeah, we have a lot of these maps are of historical interest, and of course, what people named things and in what language they chose to name them is a very important for various forms of history, especially histories of colonialism in parts of the world. So that is some of the reasons to be interested in reading text on maps. It's not all of them. Uh, but yeah, so I'll just skip ahead a bit here to mention that all this work is in collaboration with the Map Reader project, which is a project primarily based out of the UK, began at the Alan Turing Institute and is now primarily run out of Lancaster University. Um, and it with some has had partnerships along the way with other research groups working in computer vision, using advanced AI models for reading text off of maps. Um, and this is an ongoing area of research. There's a yearly challenge. Actually, they just added a large collection of Chinese text maps to make sure that kind of material is included. Um, but this is basically a case of being able to run some of the latest models and sometimes also to fine tune them to focus them on a particular domain like this kind of historical map. Um, at scale and automatically across map collections. And that's what we're working on. So we have uh, our own, in addition to the map reader notebooks, which show how to do this kind of workflow. We also have our own kind of encapsulated Dockerized app to run one of the latest text spotting models on a map, either locally or one that's being served from a mapping service. And then we built this front-end explorer to just allow you to see what kind of text has been found on the map and where. So again, we highlight the actual detections. You can search them, um, and this is useful partly because like I said, this is very difficult for a computer to do. It's somewhat difficult for a human to read text on a map, and maybe you can, especially, yeah, you kind of just squint at it occasionally and say, "Oh, where's that word going?" So you can imagine a computer that's mostly, been trained to read, well-behaved text on a page is not going to do all that on like a book page. May not do all that well, and that's where the real challenge of the technology comes in. Um, and also, it's important to emphasize or to recognize at least that searching this kind of data can give kind of a skewed view of how well the technology actually works. So the David Ramsey map collection does have this great feature to just search text on maps, and it does quite well, especially text written in Latin characters across the whole collection. It's great. You should try it out. But what you're not seeing are all the misses, all the things it gets wrong generally. And it does a bit of fuzzy matching. It finds words that are similar to the words you're looking for, but there are also a lot that it just entirely misses. And so that's why we found this kind of navigator to be useful, just to see you everything that the model thinks it's finding. So then you can also improve the model more easily once you've seen what's going on. But generally, we find this to be especially of use to researchers and scholars, like I said, who are interested in studying particular evolution, or not evolution, but certain trends in the naming conventions around places on historical maps. They may be, if they have large enough collections, they may just not be able to look at all the place names. They may actually need help searching it. But more often, they just need a way of compiling all of the names of places on maps and then applying other analyses to them. So this is something of a research aid. This kind of tool is a research aid for our researchers, whereas the searching for text on maps is more of a search and browse aid for researchers and the general public to make a historical map collection more usable. Because otherwise, if you don't index the text on your maps, all you have is the metadata, which if you have conscientious librarians with a good deal of time to do this kind of thing, they can do a lot, but obviously there's a limit to how much they can do and how much can be indexed manually. All right, so that was our brief foray into historical GIS for map collections. Now I'll move on to another example that involves using these vision language models, so very similar models, actually some of the same models that we use to transcribe the Ed Ricketts scientific observation cards from the Western Pacific coast of North America. To applying those to images, specifically to improve image captioning. So this is a challenge that a lot of libraries are facing these days, or any academic or educational organization with large image collections that are used educationally, at least especially in the United States and in Europe and other parts of the world. It's important to provide captions or alternative text descriptions of images that are used in educational contexts. And this is somewhat hard for AI models to do no matter what, but especially in historical context, it becomes more difficult. And what this particular project was exploring was how much the computer generated. So assuming you have a lot of these images and you don't have time to have people generate captions for all of them, how well can computer generated captions be improved, or how much can they be improved? If there's some other contextual metadata available that can be also included in the task that's presented to the AI model. So we're combining human input with just the AI model's ability to describe what's on an image. This is a collaboration with actually the head of our art and architecture library here at Stanford. So this is just an example using an open access image collection of Japanese illustrations from the late 19th, early 20th centuries, available through the Library of Congress in the US and also the Metropolitan Museum of Art. So you'll see a few different versions of this table, but basically what we're seeing here is how a model, I think this is just Chanwen 215, how it would describe an image given no other information other than just the image itself. There's also ground truth from this collection, actual description from a librarian, and then we have the combination. We have what happens if you give the model the description and the image. And so, it obviously does a lot better. The model makes all these assumptions that are not true. Thinks it's a Japanese woodblock, so it must be a samurai on this horse. And it isn't at all. Of course, it's an American. He's holding an umbrella, not, yeah. He's holding an umbrella, and that's clarified by the description. But what if you don't have ground truth human description? So let's say we ignore the ground truth here. This is another example from that collection. Sorry, the columns are in a different order here, but you can see just given the image only, the AI model thinks this is a Chinese illustration showing a dragon being controlled by performers. But if we include some of the metadata in the user prompt, so the sort of per item prompt that the AI model is given, it does this metadata at least includes the title, which is in Japanese. And given that just given the image and the metadata, the model does a better job of saying, okay, this is a dragon dance. It has a label. It no longer says it's Chinese because the trick here is that it's a Japanese illustration of a dance that is of Chinese origin. So it's very complicated. And yeah, and so and if the model has everything, then it does a much better, really good job of describing the image. So you can imagine this kind of work being automated to some degree, or this kind of thing helping, ideally using the same sort of interactive system that we're using for the Ricketts scientific observations. You can imagine this also working similarly. Yeah, here's one final example. This is from our great collection of San Francisco Chinatown ephemera and photographs from a particular photo studio that were from the early 20th century that were barely saved from destruction, and have been digitized. And again, we see here the tendency of the model to be less culturally informed than it should be. It says this is elegant attire that this woman is wearing, but of course they're water sleeves. She's an actress, and if the model is given a bit more contextual information from the metadata, then it can do a better job. You could also imagine just fine-tuning a new flavor of the model just for this image collection, if the image collection is large enough to merit that kind of automation. And yeah, when we're just sort of prototyping some of the other interfaces that a librarian might use to be provided with a set of sample descriptions of the images for human verification of choosing the right image, or at least avoiding choosing the right caption for an image, or at least avoiding captions that shouldn't be used. All right, so moving in a different direction, but keeping the focus on Silicon Valley and East Asia and that kind of connection, or this I should say the Bay Area of the United States and East Asia. This is just an example of another project that my team briefly worked on, which is the study of early digital typography for Chinese. Specifically, this is a really effort led by history professor Thomas Mullany, who has been studying the history of computing in East Asia with a particular focus on Chinese typology for quite a while. And this is kind of to show how research data services can contribute more directly to research via basically software emulation of recently digitized archives. So Professor Mullany has found that as materials from the 70s and 80s are discarded, especially in Silicon Valley, let's say when people are cleaning out their garages, there's this rich history of early efforts to make non-Western writing computable on systems that were initially designed for Western alphabets. That's in danger of being lost. So the Stanford libraries have been adding these materials to our collections, to the eponymous Thomas S. Mullany East Asian Information Technology History Collection. And you can see here, this is an example of one of the early systems for Chinese font design, Sinotype. And so some of these materials are actual, bitmaps of the actual glyphs for some of the first Chinese fonts that were developed at least to be used on Western computing systems. And what we actually did for this project was we found a version of the code for one of the very first font design computer programs that ran on an old Apple II, here at 2JS. And it was just written in BASIC, so we just scanned it or typed it back in to an emulator. Fortunately, the emulator is already written. We didn't have to write it ourselves. But there's a little bit of work done needed to make the pieces fit together. But now we have a working emulator of this piece of software that hasn't run since 1981 approximately. That shows how you would have had to describe and build some of the first fonts for displaying Chinese glyphs on a computer. All right, so Yeah, that was a pretty quick project, but I thought it might be of interest. Another somewhat larger scale project that we're working on that also involves, you could say, very early information technology, if not computing, and more modern computer vision, machine learning, if not artificial intelligence, involves working with piano rolls. Um, so we have a large collection of historical piano rolls. Thousands, if not tens of thousands of them. Uh, you've probably seen these before, but just to review, they are, long rolls that are meant to be read pneumatically via suction, and that actually, activate a piano so they can play a piece on a piano automatically if you have the right piano to do it. And such pianos used to be incredibly common all around the world. Nowadays, they're a bit of a rarity. When we have this giant collection of these materials that can tell us a whole lot about obviously people's listening preferences in popular culture in the late 19th and early 20th century, and also even performance practice for classical piano performance from the 19th century. These are by far, some of the earliest recordings of anyone who was living in the 19th century who was also a famous piano performer, generally from Europe. They recorded these on these fairly sophisticated reproducing rolls. Um, but just to show a bit of the processing workflow that we initially set up, we brought all of these rolls to Stanford. In this case, they were coming from Australia. We cataloged them and unrolled them, and then imaged them on this custom-built scanner for. It's actually using all of these rigs. There are a few rigs like this in the world that they're all somewhat custom. This is using an industrial fruit scanner, very high resolution fruit scanner that like scans your oranges as they go by and looks for any abnormalities on them. But it turns out it works really well for line by line scanning of piano rolls as they're rolling by. So we ended up with hundreds, and we'll eventually have thousands of these images in our digital repository, but they're images, and obviously this is piano music. I can't really tell what this sounds like. Actually, I've worked on these for so long, I probably could tell you a little bit about what this sounds like when it's played. But the point is to actually experience the full thing. So that's why we set out to build a web emulator. Yeah, a web-based emulator. So what we get is then the next step is to run some optical hole detection on these scanned roll images. And after some more web development, we eventually built this app that we call the Pianolotron, that allows you to play back a roll in real time, or any of the rolls in our collection. And yeah, thank you again for the question about the emulator. I think I'm about the basic emulator. I think maybe we can leave that till the end. The answer might be complicated, but thanks again. I really appreciate the questions. So again, speaking of the piano roll app here, one of the important things to note about it is that well, so we have, so we're working with the roll scans and the optical recognition of the perforations, which we then have to parse and, interpret according to whether they have to do with the pedals or how loud and soft the music should be, or exactly which keys are being pressed. And we also can pull in, of course, all the cataloging metadata, which, can't really be automated. Someone has to type that in to get this information here on the left. And also for more research-oriented purposes, so in addition to just letting people hear what these rolls sound like, the idea is this is a fully interactive emulator. You can change, just as you could on an actual player piano at home, you can adjust the speed and the volume, and even change the pedaling if you want. Also for researchers, for the reproducing rolls, the really fancy high resolution players for historical recordings. So in this case, we have Camille Saint-Saëns playing his own piece in the late 19th century, early 20th century. You can actually change the parameters of the emulation of the player piano. And this is what it looks like while it's playing. I don't have the audio piped through, but you can imagine what it sounds pretty authentic. I mean, it sounds like a piano playing. But this is what the interface looks like as it's playing. And this is the full pipeline. I know it's a little bit dizzying for how these things come together, but you saw the left part of it already. That we accession the collection, inventory it, and then scan the images. The scanning output goes into our Stanford digital repository where the images are made available via IIIF, and they're also cataloged. And then but on the right here is kind of our bespoke image software, and the point is that it's kind of built on top of these other the foundational library services provided by the digital repository. The digital repository also allows researchers to download all of the indexed data files, and we do create like one nice high resolution MP3 version that you can just listen to without using the app. But obviously, we encourage people to use the app because it captures much more of the actual experience of playing these roles, where you again had the ability to change the playback parameters, and people actually would do that during performance. So this is just an example of, again, how we can fit these things together, these pieces together, both fairly traditional cataloging and digital data management of in this case, images and metadata, but combined with the more experimental front end for the collection. All right, and one of these last examples is getting more into research support kind of work that my team has done using fairly cutting-edge AI models, although this also has applications to library collection, digital collection development, particularly indexing of audiovisual materials. So this is an example of a project that my team built in collaboration with Professor Michael Rao, who is a theater professor. He's a very well-known theater director and also a teacher here at Stanford, who is also interested in applications of AI to theater. And in this case, we are focusing on performances of Stanford theater productions, but we're applying in particular human pose estimation, human pose detection algorithms that are from computer vision research that sort of come from the surveillance world, and also I would say sports analytics are the most common uses, but we can also run them on these theater productions to detect what poses and also hand gestures people are making. We encode those digitally, we put them into a database. We can also index the amount of motion, obviously the number of people, the number of faces at different points in the production. We can then search for similar poses and also actions. So you can see here, there's an inferred 3D space that the algorithm is building up just from this one single frame, actually multiple frames, but they're all 2D frames. And then I select a particular pose and search for similar poses across this performance and potentially across all performances in our database. This actually developed from a research project from several years ago now that was studying variation in K-pop dance challenges on TikTok primarily. So I included this mostly in honor of the comeback of BTS yesterday, or was it 2 days ago? But in this case, we're actually comparing sort of a multimodal analysis. We're comparing different cover dances of these dance challenges using these pose estimation systems to see where they differ. And we kind of do similar things with this theatrical analysis. You can see the types of data that we're pulling in. The idea is the research agenda is to see what these models can tell us about, for example, how different theater directors tend to stage their actors, whether the computer can detect things that people wouldn't necessarily see, or to confirm or reject the conventional wisdom among theater experts about how directors happen to stage their actors. So again, you can see there's this timeline showing many different aspects: the faces, the shots, how many hands, how many bodies, how much motion there is across the entire performance, which is about 2 hours long. And then again, there's the search interface below. There's a view of the inferred 3D scene. This is kind of a visualization of how these depth estimation models see things as well. So a lot of this work is really just exploratory work to show what these models are discovering. Because if you just take the model output without really visualizing it, I think it's easy to be misled or not to understand the results that you're getting. And this is just a view of the infrastructure that we use to index this kind of data. This infrastructure actually works for any kind of, say, a wide variety of multimodal data you get from an AI model. In this case, we're working with video. We do apply some pre-processing, upscaling, and then obviously the person detectors and trackers to extract poses, shots, hands, faces, and motion. And then we run, this is the other AI piece is to generate these embeddings that would place similar poses close to each other in a particular search space. We put that all into a database that is very good at doing these searches quickly, and then we provide a front end around that. And here's just more examples of the output from this kind of search and browse system. So actually on the top here, we're searching by action. So action can include multiple frames. The descriptions are not always very interesting. This says it's someone who's talking, standing, and 5% watching, for example, or 5% carrying something. But behind that is a much more sophisticated multi-dimensional lookup system, indexing system. And on the bottom here, this is the standard pose search where we're searching for someone making this pose across, striking this pose across these various performances. We have a second interface that also incorporates some historical archetypes. So this is getting into acting theory from the 19th century, actually, about certain poses that are meant to convey particular emotions in the 19th century. And you can see some of those traditions continuing to the present in certain genres, whether it's hand poses or body gestures. In this case, we can even compare the same performance done in almost a century apart because they're both recorded on video. And we can run it through a system and see where this particular pose archetype appears in both of these excerpts around the same time. And find that actually the guy from the modern day is doing a better job of conforming to this 19th century pose than the originator of the choreography back in the 30s. So yeah, that leads to some of these research findings where we do find that if we consider three kind of famous star directors of theater from the modern day, if we take large video, or well, 10 or 11 full-length performances and run them through of each of these directors and run them through the system, they can differentiate the AI models can differentiate the directors fairly well, certainly more so than just by guessing. And then the next thing to do is to explore what they're seeing, what sort of trends they're finding or tendencies of the directors that they're finding by, for example, visualizing the search space of all these poses across with this particular system, or in this we can sort of fingerprint. I'm not sure that's the best term to use because we're talking about hands, but we can develop this profile of a performance by looking at how prevalent different hand gestures are. And we have actually deployed this system as well to augment another project that my team worked on a few years ago, which is a site to explore Japanese No theater. We have a couple of full-length performances of No that our faculty collaborators have annotated extensively with various levels. This is all done in English, so it sort of augments the quite large existing Japanese language literature describing the nuances of No and how all the different pieces come together, the gestures, the dance movements, the costumes, the masks, the music, percussion, obviously the texts, the staging, and the props. So you can see some of the interfaces here for that, building up from the elements, the music, to overall formal structures that accompany a live video of the performance, and then actual annotation of individual moments down to the second level of each performance. Yeah. Yeah, that's a great question about how pose estimation or post tracking is used in medicine. Yeah, that's definitely also an area of active research, particularly even in the medical school here at Stanford. There's some people who are researching how to use videos of people doing gestures or actions or other measurements of actually pushing on pressure plates to diagnose problems with musculoskeletal problems. So initially we thought that maybe this wasn't going to work for analyzing no theater. So in 2021, we tried these tests, and they're not catching most of the characters because they're wearing these very large costumes. The fox deity has actually thrown its sleeve over its head, which means it's now invisible. And sure enough, the model can't really see it anymore. But then we waited a couple of years longer, and a new model came out from UC Berkeley that works quite a bit better. And then just a few months ago, Meta released their Segment Anything 3D body model, which is quite good at doing this kind of thing. This kind of estimation, even given costumes. So yeah, so there's more potential for, I think, for applying this kind of analysis to other performance traditions that it initially didn't work very well with. And I think the last few minutes, then I'll just move on to our last. Oh yes, permissions from the directors and actors of the performance copies and analyzed. Yeah, that's a big important thing here. This site, I mean, it was one of the real contributions of this NOAA's intermediate site was that it was a full collaboration with the Kongo School in Kyoto who actually donated these collections and allow them to be analyzed within the context of the project. So yeah, so it's very important to get permission to share all of these things. And there are, I think if we were to do this more, certainly if we were to do this more, I would say at a larger scale, we would need to go back to the school and talk to them about what we're doing because this kind of analysis is, well, all aspects of this kind of analysis are potentially controversial. Even if you're just doing a standard analysis, you want to make sure you're using the right terminology to describe that particular school of performance. So that is an issue that definitely comes up with these kinds of analyses. The issue of using the right terms for analysis also come up in this last study analysis, which is just kind of going back into this question of how well AI models can index and describe artwork from various cultures and eras. This is initially looking at the flip side of it, which is the tendency these days to use generative AI to try to generate artwork visuals from a particular genre or era. I don't particularly like this very much, but it is a popular thing to try. I noticed that what's interesting is this model still doesn't get the feet right, or it's not very good with bird hands. But so we find it generally more productive from an archival and research perspective to kind of flip things around and just try to investigate what the models are doing, what they're finding to be resonances between two different modalities, in this case, text and image, using these contrastive models. So the first one, was from OpenAI a few years ago. That was for images and text. And this model sort of was adopted in many different areas, including astronomy, trying to find correspondences between visualized spectroscopy versus just regular imagery, so you can kind of know which galaxies you don't have to derive the spectra from because they're probably not going to be interesting. This is a different project that one of my friends worked on that involves finding correlations between chemical reactions and the genetic fingerprints of enzymes. So then you can maybe find a better enzyme for the reaction that you're trying to encourage, or the chemical result that you're trying to get. And also there's one called, in addition to CLIP, which is language image, there's CLAP, which is language audio. So finding correspondences between audio and text descriptions. And what this allows you to do is to do basically, search of non-labeled data. So if there happens to be no metadata for these pictures of mountains, you can still find them just by searching for the word mountain using this system. It's often better to do more of an evocative search, we call it, where you because this is semantic search where you give it a bunch of words that describe something you're looking for. We can also do some further introspection to see what parts of the image are responding to, or that the model thinks are most correlated with the text, the search text. And we can do this also for art styles. So I asked for visual arts of the Heian period. Of course, our collection doesn't really have much of art from the Heian period because there isn't much there, but it did find something from the Tale of Genji, which was written, a depiction, from like the 18th century or 17th century of the Tale of Genji, which was of course written in the Heian period. So that was kind of interesting. There was another project where this is actually related to a conference at the National University of Singapore that was studying the concept of Ma, which actually derives to some degree from no theater, but just, it's an aesthetic that we thought refers to negative space or pauses in performance. And when applied to images, in this contrastive method, we did find some tendency to highlight the negative space of images when told to search for the character Ma here up on the left. Although what we discovered was that depending on the model you use, you can get very different results. So some of these results here were from a specifically Japanese trained model. When we used a more generic multilingual model, we started to get a lot of pictures of rooms and interiors, and we eventually realized that's because the model is more heavily weighted towards the Chinese reading of the character, which is more associated with apartments and spaces between. These images are all again from our public access corpus from the Library of Congress and the Met Museum in New York. And the model itself, as I mentioned, was trained on basically a lot of paired language images, unfortunately, that were often just Google translated captions from English. So this leads to my final point here, which is kind of a gloss on Rich Sutton, who's a computer science professor's bitter lesson, which is basically describing the somewhat regrettable tendency of AI technology breakthroughs to happen by focusing on the process of learning rather than specific subject expertise. You can tell an AI model everything you want about chess, but it's actually going to learn how to play chess much better just by being given the ability to play a million games and learn as much as it can from that. This is similar to also eventually how language translation works. If you throw billions of words at the model, it does better than if you just try to teach it every little nuance of a particular language. He does sort of provide cushion the blow a little by mentioning that, on the other hand, we're just talking about particular abilities for an AI system. We're not talking about the actual contents of minds, which remain tremendously irredeemably complex. But it certainly has been the case in the last few years that most of these AI breakthroughs have happened through building more sort of meta learning infrastructure rather than providing expert advice to the model. On the other hand, you still need to know, specialized knowledge is still necessary, first of all, to know when the model is not working right or when the model is acting strangely, and then to understand why. So here, this shows that we can recognize that we get much better results when we used a model that's actually that trained on a Japanese trained contrastive language image model. And if we actually dig into the training data set for this collection, we find that it's not just trained on Google translated image and text pairs, but it's actually trained on a large-scale data set of originally Japanese captions. And they're not always the most profound captions. Here it's just a picture of a cat and some captions that say it's a cute cat sitting on a table or something. But it's still an actual sort of bespoke specialized data set that then does produce better results. So all those images of cats on the internet are really doing something after all. All right, so that was my final example. And I'll just end with some final thoughts here that may or may not have appeared in these previous discussions, but I think were things that I came across or learned from other people in the course of working on these projects. The first one being obviously that open data, or in the case of AI models, open weights, because you're not always going to be able to get all the data that was used to train the model, but you should at least be able to reproduce the results you get. And to do that, you need the weights for the model that generated the results that you're getting for reproducibility, predictable behavior, and ultimately for fairness and open exchange. Also, yeah, just the more you automate something, especially with AI models, the more you need to test and verify the outcomes, not less. You have to do it more. Then that privacy, yeah, obviously privacy and copyright concerns must be considered and heeded. But there are ways of provisioning services ethically, even given such constraints. I mean, that's what ethical scientific research is all about, and there are analogs in the archival world as well. Finally, hiding resources from AI harvesters, trying to keep the bots from taking down your website or overwhelming your web servers. Well, first of all, for just a matter of survival, you have to do what you have to do, but generally it's a losing proposition to just hide materials and take them off the web. It's much better, I think, to minimize the impact of that behavior, but also to participate in efforts to maximize the attribution and credit. So if instead of just hiding your materials, you can put them out in sort of an AI-friendly format, if possible, in a way that allows your institution to get credit for providing the data, then that is a win-win, or as close to one as we can get. So great question about the models that we use. The models we use for most of these experiments, we start with open source models. I should say we try to use open source models as much as possible, but generally our actual workflow is that we try the closed source models first because they're generally the best. We see how well they do. Obviously, we're not going to upload proprietary or private collections to OpenAI, but when we can, we use the best in class models out there to see the results, and then we go back and try at least open weights models that we can run locally, if we can run them locally, which also, like I said, is the only way to get reliable results. And then we see if we can do the same thing with the open source models, because they tend to be in general cases, the open source models tend to be lagging behind the other models. On the other hand, if you are only interested in a particular task, like say transcribing scientific records, you can pretty quickly, especially since the models are open source and you have a better sense of how they work, you can pretty quickly build a smaller, more targeted, more specialized model for a specific task. So that's our general approach for these systems. We almost never really create a model from scratch anymore. We certainly try to work with open source models as much as we can. So yes, that was the end. We've already gotten some questions. I've been happy to answer them. But that's the end of my formal presentation. So thank you so much for your attention and for the interest.
Thank you very much again, Dr. Broadwell, for this excellent keynote lecture. It was truly inspiring to learn about innovative projects taking place at your university, at your library, and across the wider Bay Area community. So I think these initiatives highlight the powerful potential of AI tools and creative approaches to process, manipulate, and index diverse forms of data. So I also believe that research libraries are at a pivotal moment where digital innovation has the potential to really expand our impact on research and scholarship in general. So I would also like to thank everyone who joined us today and for engaging so thoughtfully with this inspiring keynote lecture. We have now come to the end of today's keynote lecture. Thank you very much once again for everyone for coming to join us.